Soviet doctrine emphasizes the importance of rapid offensive operations in the rear of the enemy to achieve the degradation of morale and the destruction of a cohesive defense. When one considers these aims, and the history of fighting within strategic depth, there is only one formation that should come to mind. In this video, I hope to shed light on how the technology that defined the Airborne Forces came to be, as a primer for Part 2, which will focus on how these systems were used. Following the Second World War, a decision was made concerning the subordination of the strategic airborne forces. Initially, and during World War II, airborne troops were under the Supreme High Command of the USSR, though they were still considered a part of the Air Force. This would be foregone in favor of reorganization underneath the Ministry of Defense. At this time, titles such as Commander of the Airborne Forces were being re-established. In April of 1946, Colonel General B.V. Glagulev would assume the position. Alongside these organizational shifts, the Airborne Forces of the USSR would see extensive rearmament initiatives, with the purpose of giving these units a greater capability for independent operations within enemy depth, which was severely lacking as experienced in World War II. They began to receive systems increasing their ability to engage both indirect and direct fire. The operation of artillery and mortars within these units improved their efficiency substantially. In 1953, this was fully actualized. Following this, an effort to adopt improved anti-armor capabilities was pushed, seeing as this was an element which was similarly absent in World War II. It was also demonstrated during the war that airborne forces were only as valuable as the aircraft that could transport them, and therefore some of the first developments that followed this period surrounded aviation, which could effectively deliver them. Initially, these would take the form of IL-12 and IL-14, which followed the discontinuation of gliders and other less conventional means of delivery. It was later found that similarly, the parachutes employed by the airborne forces were just as, if not more, underdeveloped than their lift capability in regards to the landing of heavy equipment such as light armored vehicles. Due to this deficiency, work on improving these systems was pushed. Prior to these improvements, jumps could not be carried out at speeds exceeding 180 kilometers per hour. In accordance with the requirements of these programs, this rose to 300 kilometers per hour, which allowed the airborne forces to keep up with the development in transportation at the time. This would culminate in Dolgov and Andreev receiving Hero of the Soviet Union after a record-breaking jump from the stratosphere. Andreev would fall for 270 seconds before opening his parachute less than a kilometer above the ground. Dolgov would open his parachute earlier, though unfortunately died due to the depressurization of his equipment. At this time, work on multiple parachute systems for heavy equipment saw simultaneous development, which would culminate in the adoption of PP-127, which had a max load of 4,600 kilograms in the late 50s, allowing for the airborne forces to effectively land artillery, vehicles, radio stations, and engineering equipment, as well as chemical defense systems. Though the PP-127 would soon be replaced by the superior PP-128, which had a max load of 6,700 kilograms. This would not satisfy the airborne forces. Work began on new means of landing heavy equipment at greater speeds and capacities almost immediately afterwards. The introduction of retro-rockets as a result of this program served as a quantum leap in the capabilities of the VDV, which was finally breaking from the conventional understanding that they would be of most use coordinating closely with ground forces for rapid development of offensive operations, especially when water obstacles were involved. The rationale for this doctrine was a result of limited amphibious elements at the time, which did not allow for the transfer of entire divisions in a reasonable period, only small raiding detachments. The VDV would capture bridges and crossings and hold them until the main body could sort out an effective means of advance. or strike at the rear of a well-prepared defense as the crossing occurred. This doctrine soon developed into the idea that the airborne forces would instead be used to encircle an enemy, which was being engaged by the main body. Though after some debate, this was revised into the concept of employing the VDV as a decentralized element in the rear of the enemy, to disrupt a withdrawal if they were decisively routed by the main body, setting up ambushes and enacting raids on fleeing convoys, as well as cutting off reserves. As their capabilities grew, so did the scope of their objectives, and by the 1960s it was solidified within military thinking that the VDV was best used to disrupt strategic elements such as communication centers, command posts, airfields, warehouses, nuclear deliverance, and political assets. This shift was accompanied by a great deal of experimentation, which worked to diagnose the issues which may be present in the equipment assigned to the VDV when accomplishing these tasks, which ultimately resulted in the adoption of the BMD-1. This influenced the foundation of the airborne forces in a fundamental sense, ushering in the era of mechanized airborne composition. At the same time, the VDV's transportation saw revisions seeking to keep up with these ideals, which brought about the AN-12 and AN-22, as well as the IL-76 later down the line. Innovations in both mechanization and airborne capabilities coincided with success in the application of retro-rockets, which made it possible to transport an assortment of modernized, heavier equipment within the enemy's rear. These elements were accompanied by a wave of reforms in the late 60s and 70s, which worked to redefine the airborne forces as a specialized, elite element within the military system. This translated to training and conscription practices as well. Airborne forces were to be politically reliable. They were to be well-versed in navigation, hand-to-hand combat, largely immune to psychological subversion enacted by the enemy, medical affairs, parachute operations, and have a superb mental and physical fortitude. Under this new regimen, airborne forces would only accept the bravest of conscripted individuals, who would begin their training with parachute qualifications while being taught high moral standards such as determination, courage, and the importance of not losing one's nerve, even in the most difficult of situations. Intense training preceded this. Almost all classes were conducted in simulated field conditions, where subjects such as reconnaissance and land navigation were engaged. Former service members within the VDV often note the lack of rest or relaxation from exercises as a primary critique. These revisions would continue into the mid-1970s. But the first large-scale endeavor, which featured the improved airborne force, excluding the BMD-1, was Dnieper 67, during which several landings were conducted aimed at seizing elements in the rear of the enemy. The first unit to land during this demonstration was a reconnaissance unit, which worked to capture a landing zone as fixed-wing aircraft suppressed defenses as the forward element arrived, followed by AN-22s carrying heavier elements. This was also one of the first demonstrations of retro-rockets in simulated combat conditions. In only a few short minutes, thousands of airborne forces had been delivered. Following the operation, observers writing for Izvestia remarked, "It must be said that the paratroopers are warriors of boundless courage and bravery. They never get lost. They always find a way out. The paratroopers are proficient in various modern weapons. They wield them with artistic skill. Each fighter of the winged infantry knows how to fight 1 against 100. During the days spent on the exercise, we had to see a lot of skillful actions, not only by individual soldiers and officers, but also entire units and formations. We have witnessed the art of using military equipment in the most difficult combat conditions, but perhaps the strongest impression was left by the airborne troops, which were led by Margalov. Their soldiers showed such courage and high training as well as initiative that it can be said that they very much so live up to the standards and military glory of their fathers and older brothers, paratroopers of the Great Patriotic War." In later exercises engaged that same year, the airborne forces found themselves encircled by enemy armor before reinforcements could be delivered. But thanks to the initiative displayed by Major Belchikov, the battalion managed to break through the encirclement. Deputy Defense Minister Moskalenko, who observed these actions, stated, "The tactics and ways of solving combat tasks of the paratroopers are different from the actions of, say, motorized infantry or tankers. Paratroopers fighting behind enemy lines have no neighbors, on either their left or right. The rapidity of blows, mobility, and the ability to impose one's will on the enemy, factors that are important in any battle, here acquire a special role. The battalion and its attached units cope with the task. The pace of the offensive, and especially the combat prowess of the paratroopers, was high. The morale and combat training of the paratroopers is respected." The integration of initiative in regards to the tactics employed by the VDV was one of the greatest reforms to their operation following World War II. This was actualized through impressing creativity in regards to problem-solving within each lesson, which worked to cement this element as a fundamental facet of the functionality of each paratrooper, as he may be forced to engage the enemy alone. After the Second World War, the development of armored vehicles for use within the airborne forces was a constant endeavor. In 1946, at No-92, work would begin on a system to fulfill this requirement. The early concept mounted a 76mm gun on a light air-deployable chassis that was developed by Mitishi Plant No. 40. In 1947, the chassis, designated Object 570, was completed. No-40 would receive 2 prototype LB-76S guns from No-92 later that year, allowing for the first functional prototype to be completed in December. In 1948, testing would begin, and by the end of that year, the LB-76S was approved for service and would receive the designation D-56C. 4 prototype vehicles would see further tests conducted in 1949, before the vehicle was accepted into service as ASU-76. ASU-76 would operate the OP-2-9 sight, which would allow for direct fire engagements. The chassis was protected by 13mm of armor, which provided resistance against fragmentation and small arms fire. The vehicle would mount the GAZ-51E engine with a 4-speed gearbox. To increase cross-country mobility, the vehicle's rearmost road wheel is lowered. The vehicle would operate the 10RT-12 radio for communications and feature an intercom system. Despite its revolutionary status as the first airborne fighting vehicle produced in the USSR, it did not enter mass production. This was primarily a result of limited lift capabilities experienced at the time. Initially, the vehicle was to be landed using the IL-32 glider, which was produced in 1949. This device would carry a maximum of 7,000 kilograms, meaning it could transport 1 ASU-76 or 2 ASU-57s. While promising, the aircraft designed to deliver the system, that being IL-18, proved unsatisfactory and did not enter service. A project that would transpire in tandem with the previously discussed system would be ASU-57, which sought to develop a lighter alternative to complement ASU-76. The 57mm 113P automatic gun that the vehicle was to operate was interestingly not developed for the airborne fighting vehicle, but for the Yak-9-57. However, the installation of this gun proved problematic and did not meet program requirements. As a result, the CH-51 compact 57mm gun was chosen and developed between 1948 and 1958 at No-106, and was initially designed to improve the ZIS-2 anti-tank gun. Within the ASU-57, the gun could move 8 degrees positive or negative horizontally and -5 to positive 12 degrees vertically. The gun could operate high-explosive fragmentation round with a projectile mass of 3.75 kilograms, conventional armor-piercing ammunition with a projectile mass of 3.14 kilograms, and armor-piercing discarding sabot with a projectile mass of 2.4 kilograms. At 0 degrees, the armor-piercing ammunition supplied to ASU-57 was capable of penetrating 85mm at 1,000 meters. The APDS available to the system was significantly more effective and offered 100mm of penetration at 1,000 meters, as well as 72mm at 2,000 meters. In 1954, the CH-51M would replace CH-51, which featured an improved muzzle brake. No-40 would propose a lesser-known prototype before developing the ASU-57, which would mount the 57mm 113P automatic gun. The issue with this gun was that it had a pathetic muzzle velocity of 720 meters per second when firing UBR-271. The only advantage it offered was an increased fire rate. The vehicle was equipped with a 4-cylinder, 50-horsepower engine and carried 51 rounds, most of which were stored within the fighting compartment. Unlike the ASU-57, this vehicle was made of steel and used little aluminum in the construction. In 1949, VRZ No. 2 would propose a 3.4-ton vehicle that mounted the CH-51 compact 57mm gun, combined with the OP-2-50 sight and SG-43 machine gun for anti-infantry application. The vehicle would carry 30 rounds for the main gun and 400 for the machine gun, operated 6mm of armor, employed the GAZ-51 engine with 70 horsepower, and arguably the most appealing facet was amphibious. The system employed a propeller to allow for speeds of 7 to 8 kilometers per hour when afloat. Unfortunately, this project would be a failure as it demonstrated poor cross-country capabilities. Object 572, which would later become ASU-57, was created at OKB-40 and would feature the same CH-51 compact 57mm gun found on VRZ No. 2's proposal. Between 1948 and 1949, the vehicle would pass field tests with flying colors. ASU-57 entered service in 1951, the same year it began serial production. The system would make its first public appearance in 1957. Inside the vehicle, an SG-43 could be found, and eventually an AKM. The vehicle employed thin aluminum armor. Some steel was used, but it was sparing to keep the weight down. ASU-57 operated the 4-cylinder M-20E, which provided 50 horsepower at a speed of 3,600 RPM. This engine was also used in the GAZ-69. The reduced weight of ASU-57 contributed to its exceptional cross-country performance. The vehicle had a ground pressure of only 0.35 kgf-cm², which ensured its functionality within heavy snow cover and swamps. ASU-57 was equipped with the TPU-47 intercom system, which allowed the crew to effectively communicate with one another, and a 10RT-12 radio. The radio was located in front of the commander's position. In 1961, the 10RT-12 and TPU-47 were replaced by the R120 TPU and R113, which afforded the ASU-57 a communication range of 20 kilometers. Following ASU-57's introduction, they were organized into anti-tank companies, featuring 9 vehicles. Every airborne regiment operated such a unit to combat medium tanks at the time. The moment ASU-57 entered service, an amphibious variant was being devised, under the designation Object 574 or ASU-57P, which was first built in 1952. 4 prototypes were tested between 53 and 54. This modification weighed 3.35 tons and significantly expanded the hull to allow for buoyancy to be achieved. The engine installed on the standard ASU-57 was improved to offer 60 horsepower, which would supply sufficient power to cross water obstacles. Interestingly, ASU-57P would feature an improved gun, known as CH-51P, which improved the fire rate to 12 rounds per minute and introduced a more advanced muzzle brake. Initially, the vehicle was to feature 2 propellers, but this design reduced traction when coming ashore, and therefore a new system was employed that used the gearbox to generate power to a single propeller. A heat exchanger was also installed which cooled the vehicle while afloat, and dispersed the heat into the water. Unfortunately, this vehicle would remain a prototype. In 1955, the Airborne Forces were in need of a new combat vehicle, with a more powerful gun to engage modern threats. To meet these requirements, the ASU-57, equipped with a B-11 107mm recoilless rifle, was developed. This design was, for obvious reasons, a failure. To land ASU-57, the Yak-14 heavy glider was developed in 1948, coinciding with the production of Object 572, which was delivered by IL-12D. Experiments with Tu-4T were considered, but this proved unsatisfactory. With the adoption of AN-12 in 1959, the capabilities of ASU-57 were greatly expanded. Parachutes to deploy the ASU-57 from this aircraft were developed at No. 468 in Moscow. Here, the MKS 4-127 and MKS 5-128R multi-dome parachutes were conceptualized and designed. When employing these systems, the ASU-57 was secured to the PP-128-500 landing platform, later P-7. The combined weight of the platform, parachute, ASU-57, and associated provisions was 5,160 kilograms, 2 of which were deployed from a single AN-12 with a descent speed of 7 meters per second. The ASU-57 could be lifted by an Mi-6 as well. Before I can even tell you about this vehicle, I need to make a strong disclaimer. No one actually agrees on what this thing is called. All of the Soviet documents say Su-85, but many other militaries, notably Poland, who used this vehicle, refer to it as the ASU-85. Here is a clip from the 1966 Warsaw parade where it is stated in the official narration to be ASU-85.
Działa samobieżne ASU-85 przystosowane do transportu powietrznego.
And here is a Soviet document that uses Su-85. Your guess is as good as mine. The Su-85 was developed to fulfill a wide array of tasks and was not designed with the express purpose of serving as an airborne fighting vehicle. Because of this, they were to see integration within motorized rifle, tank, and airborne formations, which were of course the primary consideration of its development. It is best to consider Su-85 akin to Kanonen Jagdpanzer present within the Bundeswehr at this time. Object 573, which would become the Su-85, began development in 1953 at the Matishi machine building plant, and entered service in 1956. The vehicle mounted the 85mm D-70 as its main gun, which was developed by F.F. Petrov at plant number 9, produced at number 75. The gun could move 15 degrees horizontally in either direction, and from -4.5 to +15 degrees vertically. For direct fire, the TS-HK-2-79-11 was employed, and for indirect fire, the S-71-79. When used in this way, it is stated that a range of 13,400 meters could be achieved when employing OF-372 high-explosive fragmentation. For engagements in night conditions, the Su-85 was equipped with the TPN-1-79-11 and L2 IR illuminator. The ammunition employed by Su-85 included UBR-372, 3UBK-5, and OF-372. UBR-372 employed the BR-372 armor-piercing tracer, which had a weight of 9.3 kilograms, which could penetrate 180 to 200 millimeters at an angle of 60 degrees, with a distance of 1,000 meters. The round has an exit velocity of 1,005 meters per second. UBR-372 makes use of the KV-5 percussion primer, due to the fact that the round exceeds the maximum pressure KV-4 is capable of withstanding. In many regards, the round is identical to BR-367, and employs the same base fuse. The dimensions of the ballistic cap are indistinguishable, with the only difference being the wider copper obturator and driving bands present on BR-372. This modification marginally increased the weight of the shell. While this round was capable of easily defeating tanks such as Centurion Mk2, it stood no chance against the upper glacis of M48. It must be noted that despite this, BR-372 was still capable of penetrating M48's lower glacis at a distance of 2,400 meters. 3UBK-5 operated the 3BK-7 heat round, which shares many of its design components with 3BK-2. 3BK-7 included 6 bladed stabilizer fins, with a steel slip ring, which departs from 3BK-2 in its location and through the use of a nut as opposed to a wedge collar to secure the ring, as well as the GPV-2 piezoelectric fuse. Compared to earlier systems such as 3BK-2, 3BK-7 had a higher muzzle velocity, and was lighter due to the use of the AIX-2 explosive charge. The round is designed to reduce the influence of rifling, but not eliminate it entirely. 3BK-7 uses a copper obturator band instead of a iron ceramic band found on 3BK-2. These changes assisted in reducing the weight of the projectile. 3BK-7 penetrates 240 millimeters of RHA and poses a serious threat to MBTs in service at the time of its introduction. For anti-infantry application, an SG-43 could be found inside, alongside 250 rounds for the machine gun, dispersed across 8 boxes. 1 AKM with 300 rounds, 15 F1 fragmentation grenades, and an SPSH-44 flare pistol. Su-85 protected the crew from small to medium caliber armor-piercing ammunition. An emergency hatch was present on the floor of the fighting compartment for immediate evacuation. Much to the design team's chagrin, the YAMZ-206V two-stroke diesel engine was employed within the vehicle, which had 210 horsepower and an RPM of 1,800. The engine was started electrically, and employed a relatively large liquid cooling system to offset its poor performance. It was impressed upon those developing the system that Su-85 had to be designed around this engine. As a result, the cross-country performance of the vehicle was diminished, albeit marginally. The engine was positioned in such a way that it offset the weight of the gun. Su-85's mechanical transmission featured a 5-speed gearbox with 5 forward and 1 reverse gear. A torsion bar suspension was present that incorporated hydraulic shock absorbers. Su-85's commander employed the TKN-1T night observation device, which was independent from the gunner's optic. For the driver, TVN-2 was available. When outside of night conditions, the commander operated the TNPK-240A, which had a maximum magnification of 8 times. The crew communicated using the R120 TPU intercom system, and had access to an R113 for long-distance interaction up to 20 kilometers. To obscure itself on the battlefield, Su-85 operated 2 BDSH-5 smoke bombs. In some cases, these were repurposed to allow for the transportation of fuel drums. Each airborne division operated 31 Su-85s organized into assault gun battalions, which were delivered by an AM-12. The Su-85 was severely constrained by the fact it was intended to be landed and unloaded on a prepared runway, after which a PP-128 would arrive, supported by an MKS 5-128M multi-dome parachute, which contained a Gaz-66 loaded with boxes of ammunition for the vehicle. In 1961, the inability to conduct high-altitude drops using Su-85 into the rear of the enemy was becoming a factor that limited the application of the Airborne Forces, and as a result, a solution had to be devised. This would come in the form of the P-16 landing platform, which could support a maximum weight of 21,000 kilograms. This made it possible to deploy Su-85s from AN-22s. While this development was indeed important, it coincided with the development of the BMD-1, which would soon make the Su-85 obsolete.
Вихрем гнет десант, срываясь ливнем внезапно вниз. И только ставка по жизни в жизнь. ВДП, с неба привет, ультрамариновый напад берет. Дельник с волной и море погон, с небом навеки десантом ручен. ВДП, сколько побед, из парашютов белый букет. Радугой мирной парят купола, слава десанту, честь и хвала.
The BMD-1 was first conceptualized due to the lack of an amphibious vehicle that could be supplied to the airborne troops. Volgograd Tractor Plant was chosen to design and produce the system. This is due to their experience in the production of light armored vehicles. Astrov Design Bureau wished to usurp the contract, seeing as they had spearheaded the previous generation of ASU-57 and Su-85. At this time, Volgograd was in the process of updating the aging PT-76, and found that the strict requirements, which were demanded by both programs, shared many facets. Therefore, BMD's distant ancestry is tied closer to PT-76 than BMP-1. The BMD's unique requirements were that it had to be light enough for AN-12 to carry two of them, be capable of employing the P-7 and MKS-760 multiple parachute system, as well as share its armament with BMP-1, which was a contract Volgograd competed for years prior. The BMD was to have a crew of 2 and transport 5 paratroopers internally. This would be diminished to 4. It's important to note that this isn't a significant difference from a standard motorized rifle squad, considering those were only 5 men strong, when excluding the platoon marksmen. There were also to be firing ports along the hull to allow for defense from any direction the system may be engaged from. It was to share similarities to the BMP-1's power plant and operate a water jet propulsion system. The first prototype to see similarities to BMD was Object 911, which saw propositions for a rear engine and transmission configuration, and the ability to carry 6 dismounts. The vehicle was to feature a 2-man turret alongside a bow-shaped front which would improve its amphibious capabilities. Similarly to BMD, Object 911 would concentrate the dismount compartment towards the front of the vehicle, with 6 sitting behind the turret, along with firing ports to the rear and sides of the vehicle. The system would feature a unique hatch design, forcing the crew to dismount over the engine, being wide enough for 2 to dismount simultaneously. Object 911 would operate a mechanical transmission, with a 2-disc main friction clutch and a gearbox containing 2 clutches, as well as 2 planetary gears, alongside 2 hydrojets. These were almost identical to those found on PT-76. The vehicle would also employ a track suspension with a rear drive sprocket and front idler, and 5 road wheels, which were identical to those found on PT-76. Like the BMD, pneumatic suspension was used, which allowed the vehicle to raise and lower its height from 426mm to just 96. The armament would be identical to that of BMP-1 as per program requirements. The vehicle would functionally depart in its more niche characteristics. Object 914 would be a more conventional proposal, and was the first prototype to be air transportable, though it could not be dropped from altitude. The vehicle would have a crew of 10, factoring in dismounts, and would operate a nearly identical layout to that of BMD in regards to the position of machine gunners relative to the driver. Though unlike the BMD, the armor would be high-hardness steel. V6M diesel engine was employed, which was located to the rear of the hull. Similarly, a 2-disc main friction clutch and gearbox with 2 clutches would see integration. A conventional torsion bar suspension was employed, as well as hydraulic shock absorbers. The second prototype would see the integration of hydraulic track tensioning. Object 914 would employ the same water jets as Object 911. Finally, Object 915 came along, which actualized each requirement. The vehicle was made of an aluminum alloy, ABT-101. This material was easier to repair in the field compared to alternatives that required heat treating following argon welding. ABT-101 is composed of 91% aluminum, with the other 9% being largely zinc with small quantities of magnesium. ABT-101 has a hardness of 145 bhn. Object 915 protected the crew from 12.7mm armor-piercing munitions along the frontal arc, and 14.5mm on the turret. Along the sides, the vehicle was rated for 7.62. After ballistic tests conducted in 1972, it was found that BMD-1's front hull and turret were immune to 23mm BZT from a distance of 500 meters, when shot from the frontal arc. To ensure proper amphibious capabilities, the hull is quite narrow and has a bow-shaped front. There were 3 TPNO-170 optical devices installed in the driver's compartment, which feature electric heating to prevent fogging. This is engaged through a conductive layer of glass glued to the front planes of the prisms. Thermal resistors are soldered into the prisms, acting as temperature sensors. The commander's optics are reinforced to prevent penetration from shrapnel. In front of the commander's seat is a machine gun with TNPP-220A sighting device, which is similarly electrically heated, and has 30 degrees of observation, and TNPO-170 observation device. There is a second machine gun located on the other side of the driver, who has access to TNPP-220A. Dismounts have access to 2 TNPO-170 devices and an MK4S periscope, which is near the rear hatch. This provides an unmagnified picture, though it could be adjusted along the vertical axis. This periscope could be elevated by 18 degrees and depressed by 12 degrees. The hull is equipped with headlights, side lights, a wave-deflecting shield, front and rear mudguards, and water jet propeller flaps, as well as a radio antenna, landing gear, mounting equipment, towing hooks, and a device for transport on a trailer, alongside 2 boxes for spare parts, a crowbar, shovel, and emergency buoy. The engine transmission compartment is located to the rear of the hull and is isolated from the middle compartment with a sealed partition. The engine is a V-shaped 6-cylinder 4-stroke diesel 5D20, which is liquid-cooled. This system is almost identical to BMP-1's engine, but 5D20 employs a different cooling and ventilation system. The engine has only 240 horsepower, which is 60 less than BMP-1's, though this does not limit the system considering its weight. The engine uses an electric starter or a backup air intake system, with the introduction of a compressor driven by the engine. The air intake system became the main option in 1973. To facilitate starting at low temperatures, the engine is equipped with an electric nozzle heater included into the cooling system. The fuel system includes 3 tanks located in the engine transmission compartment. The air purification system is 2-stage with a cyclone block in the first stage, filter cartridges in the second, and automatic dust removal. To increase the safety of tackling water obstacles, 2 connected valves are included in the engine air intake system, providing air intake when submerged through the center compartment. The engine has an ejector-type cooling system which also provides ventilation for the engine compartment and dust extraction from the air cleaning system. The transmission is mechanical, consisting of a 2-disc main friction clutch. There are 4 forward and 1 reverse gear. The 3rd and 4th gears are synchronized. The system also includes 2 coaxial single-stage planetary gearboxes and 2 clutches. Track tensioning is done with a hydraulic drive. The suspension system is pneumatic with hydraulic shock absorbers. The suspension consists of a pneumatic spring, leveler, balancer, and travel limiter, made in the form of a stop with a rubber cushion. The return rollers also have a pneumatic spring, which works as both an elastic element and as a hydraulic shock absorber, as well as an actuator when changing the vehicle's ground clearance. This mechanism also holds the return rollers in the appropriate position, when preparing the BMD for jumps and when afloat. This system involves 2 cylinders. The first cylinder is divided into 2 chambers by a piston, one which contains nitrogen gas, and the second is filled with a mixture of transformer and turbine fluids, with a 50/50 mix. The volume of these oils can be adjusted, and as a result the clearance is changed. The chamber in the front of the piston is filled with oil and is connected to the chamber in the pneumatic cylinder, as a result of which the piston moves and the gas is compressed. During its return stroke, because of the compressed gases having expanded, the oil returns and pushes the piston to its original position. Valves allow the return stroke to operate higher fluid resistance than during the forward stroke. The clearance can be controlled from 100 to 450 millimeters. The change in clearance was originally to be used only when preparing the vehicle to be loaded onto an aircraft, but the BMD's ability to change its height gave it significant advantages in the exploitation of cover and concealment, in ambushes and defensive positions. Amphibious capabilities are provided by water jet propulsion, consisting of 2 water jets. There are 2 pumps with electric motors that serve to pump out water and displace the system. The vehicle is armed with the 2A28 smoothbore low-pressure cannon, which was designed to allow ammunition compatibility with Airborne Forces who employed the SPG-9, an early requirement that did not function in reality. The 2A28 has a barrel life of around 1,250 rounds. The weapon is fired electrically, though a backup mechanical striker also exists. The fire control system of BMD-1, like BMP-1's, offers the shooter a reliable chance of a first-round impact against armored targets at up to 800 meters. the probability of destroying an APC with the 2A28 from 500 meters is roughly 80% in the first 2 rounds. Against a stationary tank at 500 meters, the percentile is 70%, though at 800 meters, the chances degrade significantly to only 50%. At 200 meters, the PG-7V is capable of hitting a tank with a roughly 90% chance of impact, cementing the vehicle's role as an ambush weapon. The primary ammunition supplied to BMD-1 is PG-7V, later VM, and OG-15V. PG-7V combines the PG-9 fin-stabilized assembly with the PG-15P propellant charge. This munition had superior ballistic performance as well as penetration when compared to 76mm heat fired from the PT-76's D56T, and is capable of reliably destroying barriers with equal effectiveness to its contemporary. The maximum penetration PG-7 is capable of achieving is 346mm, which is more than enough to defeat M60A1, Leopard 1, AMX-30, and Chieftain frontally, though it was less capable against M60A1 and Chieftain when compared to Leopard 1 and AMX-30. Once the heavier OG-15V entered service, it was issued to BMD-1. The OG-15V is subsonic and operates smaller stabilizing fins, and is significantly more capable than the 76mm on PT-76 against light-armored targets and barriers. OG-15V had superior fragmentation effects compared to its contemporaries. This round's downside is its inferior range compared to PG-7V. Later OG-15VM would enter service, which would improve its incendiary capability and explosive effect. Object 915 would successfully pass trials in 1967, and was praised for its high degree of cross-country mobility. The accuracy of firing the main gun on the move was significantly increased compared to BMP-1 due to the hydropneumatic suspension system. The vehicle was also superior in its amphibious capabilities when compared to BMP-1, in regards to effectively and safely exiting and entering water. It held further advantages. After its adoption, the BMD-1K would enter service, which supplied the vehicle with a second R123M. There is an antenna filter, which allows both radios to operate on a single antenna. Alongside R124, an AB-0.5P-30 gasoline electric charging unit, a GPK-59 gyroscopic course indicator, a heater and a fan for the fighting compartment, and GO-27 chemical reconnaissance device were also installed. The heater, fan, and GO-27 were standard across all units. BMD-1P would begin development soon after and integrated 1PN-22M2, which included markings for firing OG-15V, stamped road wheels that were hollow, which served to improve buoyancy, and 9K-111. All previous systems were upgraded to BMD-1P standard. Later, 9M113 would be adopted and employed. There are some sources which state that 9K-111 and 9M113 would be carried in tandem in this transitional period, where there was one 9M113 and two 9K-111, but I believe this was later standardized to only use 9M113. The missiles may be removed and employed separately from the vehicle on tripods stored within the system. BMD-1P was later affixed with 90 V2 Tusha smoke system, according to some sources. R173P and R174 radios would later be installed on BMD-1PK. By the mid-80s, increasing the lethality of the BMD-1 was seen as an important step in keeping the system relevant. As a result, work on BMD-2 began. The 2A28 did in some regards struggle to engage smaller targets, especially those on the move. And there was also the ever-present threat of a rotary wing aircraft, which would cause problems for airborne forces who operated diminished anti-aircraft measures compared to their conventional contemporaries. Initially, there were proposals for a lengthened 73mm gun, which was tested on BMP-2's competitor, Object 681. Though the success demonstrated by 2A42, which was an open-bolt, gas-operated autocannon with a short-stroke recoiling barrel mechanism, resulted in the adoption of this cannon instead. As a result, accuracy against weapon teams and mobile targets was drastically improved, and the system could still threaten second-generation MBTs from the sides and rear. The new turret restricted the use of 9M14, though by this point 9K-111 and 9M113 had already been fully integrated, and 9M14 had been retired. The ability for the 30mm cannon to engage air targets with its high degree of elevation was exceptional. This was only bolstered by its fire rate, which could be shifted from 200 to 550 rounds per minute. BMD-2 finally ushered in an electro-hydraulic stabilizer in the form of 2E36-1, which was dual-axis, which had both semi-automatic for anti-aircraft engagement and automatic modes. The accuracy of the weapon allows it to engage ATGM teams with a 100% chance of destruction within 15 rounds. BMD-2 operated the BPK-142 sights found on BMP-2. This optic has a fixed magnification of 5.6 times in regards to the day channel, and is stabilized. The system includes a stadiometric rangefinder and passive as well as active night vision, which has a detection range of roughly 900 meters for tank-sized targets. Interestingly, when firing the 30mm cannon, BMD-2's turret has a tendency to rotate ever so slightly right. This is a symptom of the way in which 2A42 is mounted. It is negligible, and only an issue in long continuous bursts. The BMD would later inspire an entire family of vehicles that I will discuss later. BMDs may be transported in pairs of 2 in both Mi-26 and Mi-6. When it deployed from an aircraft, the BMD falls at a rate of 5 to 6 meters per second, and crews are often dropped directly behind them. The system included a locator so that crews could find them without complication. In 1971, General Margalov decided the Airborne Forces would benefit from BMDs landing with a limited crew inside of them. Obviously, there was a great deal of concern, and the project was scrutinized for its lack of reason or serious consideration of the dismount's safety. Initially, the test would be denied entirely, but exceptions would be made if a proper staff could be assembled to observe and manage the endeavor. The State Research Institute of Aviation and Space Medicine would begin preparing with tests that sought to determine how such a landing would affect the crew. Here, a new issue would arise, chief among them being the inability for the crew to save themselves if the landing was doomed to fail. When questioned about who would conduct these landings, Margalov immediately volunteered, but Grechka refused to endanger him. As a result, Margalov's son would be selected, who understood the importance of the project and was personally working on the system at the Scientific Technical Committee of the Airborne Forces. Equally as enthusiastic was Leonid Gavrilovich Zuyev, who would join Marshal Kulikov in the drop. After many preliminary experiments using sensors to test the impact speed, some involving animals and others dummies, the landing system was considered safe for volunteers. Before the test could begin, in 1972, simulators were developed to prepare the team for the experience and procedures that were expected of them. At this time, Grechka would once again halt the program, citing fears that these systems could significantly endanger the airborne forces. He would have to be convinced yet again that this was indeed a good idea by Margalov before he would allow the program to continue. The simulators proved vital, as following their application, many candidates for the test would be excluded after their spines were examined and determined to be unfit for the extreme parameters presented by the exercise. Testing of the Centaur landing system was to be engaged in 1973. The crew was to land in the vehicle, unmoor the BMD in just 2 minutes as automatic pyrotechnic unmooring was not employed for this test, before conducting firing drills while on the move. On January 5th, the jump occurred and the crew miraculously survived. During the tests, Margalov kept his service pistol loaded so that he could end his own life in the event of his son perishing in the exercise. Later tests would be conducted and similarly, the crew survived. Centaur would be quickly replaced with Reactor in 1976, which is literally a combination of reactive and Centaur, which I find quite funny. This variant used only one parachute, which would primarily serve to align the BMD with the retro rockets. This was more effective as the parachutes did not have the chance to cover the vehicle following the landing. The descent speed was 4 times higher, and in many regards, Reactor was significantly safer. The only complaint leveled against the system was that the retro rockets were quite loud and startled the crew. Reactor also increased the readiness of the airborne forces by being attached directly to the BMD, meaning no preparation was needed before loading the vehicle into the aircraft. The speed of descent experience when using Reactor ensures that the vehicle is only visible for an exceedingly short period of time, and therefore the location in which it will land is difficult to pinpoint. The first unit to test the new landing system was the 76 Guards Airborne Division. This test was rather unfortunate as the crew was supposed to be dropped in snow to reduce the shock endured by the first experiment, but due to the wind conditions on that day, they landed on a small patch of ice. Despite this, the mission was successful and the evaluation would result in the system entering service that year. From 1973 to 1991, and these numbers are disputed and different in many sources, some corroborate this, but there's more that corroborate it than don't, so I'm using this number. The Centaur and Reactor landing systems were used over 100 times, and every unit had to qualify on them. Airborne forces equipped with the BMD were provided with extreme degrees of cross-country mobility, as well as massive firepower advantages over threats they expected to encounter. This capacity for rapid shock attacks and incredible anti-armor capabilities was unrivaled throughout the 70s and 80s, which drastically increased the capability for the airborne forces to seize strategic terrain and complete objectives, while offering a unique scope for raids at considerable distance and momentum. In 1969, the USSR Council of Ministers and the Airborne Troops Scientific and Technical Committee drafted proposals for the design and eventual adoption of an armored personnel carrier that would complement the BMD-1. Work on this system began at Volgograd tractor plant under the supervision of A.B. Shabalin. The most important requirement that was almost immediately outlined for the program was that this new vehicle had to preserve much of the BMD-1's components and characteristics, to ensure a great deal of parts compatibility. This proved difficult, and as a result, after much deliberation, it was decided that lengthening the hull of the vehicle was an acceptable adaptation. The BMD-1's extraordinarily compact design made it difficult to significantly increase troop carrying capabilities without this addition. This was problematic, as lengthening the vehicle would reduce lift capabilities, and would more importantly require parachutes in service at that time to be redesigned. Luckily, this project would coincide with the development of the IL-76, and new advanced landing capabilities, which would alleviate these concerns. Initially, the vehicle was to feature a remote-controlled machine gun, but the turret in which it was housed proved problematic, and interfered with the landing and dismount process. This also diminished the storage of ammunition inside the vehicle. Object 925, as it was designated, would begin state tests in 1973, and would be adopted in 1974, after which it was designated BTR-D. In service, the vehicle would fill a vital transportation requirement, which had not yet been realized. The BTR-D could transport material, evacuate wounded personnel, and ferry infantry. Due to the importance of this vehicle, each airborne unit would receive a company of BTR-Ds, and all engineers subordinate to the Airborne Forces would be issued them. The BTR-D carried a total of 14 passengers, 10 F-1 fragmentation grenades, multiple ammunition storage boxes for D dismounts, 2 RPG-16s, 2 RPG-7Ds, 2 RPKs, 21 VOG-25s, 5 magazines for each of the cruise rifles, 26mm flares for the SPS-H-44, which were 5 per gun, and 2 man-pads. Dismounts ride on 8 folding quick-release seats. The communication equipment, observation devices, and chemical protection measures on board are identical to those found on the BMD series of vehicles, due to the reduction of proprietary parts outlined in the program requirements. BTR-D can be modified into an ambulance, with an easily affixed package that allows the vehicle to accommodate 4 stretchers. To engage this, the seats are removed and stretcher brackets are installed. The stretchers are stacked in pairs on the right and left side of the troop compartment. To retrofit the BTR-D to support the transportation of 2 200-liter drums, which can be filled with fuel or lubricants, all the seats are removed except for 3. In this configuration, the vehicle can also be made to carry 12 boxes of ammunition. In 1975, airborne regiments would receive the confusingly named BMD-1 KSH, which saw the commander's station rearranged, among other changes, to accommodate 2 R-123 radios, 2 R-111 radios, and 1 R-130 radio. R-123M and R-111 possess the ability to engage and automatically switch between 4 predetermined frequencies, and can operate simultaneously. Staff officers are provided with 2 tables so that they can more comfortably conduct their work. A similar vehicle, BMD-1R, is equipped with the R-161A2M very high-frequency radio, which can provide clear communication up to 2,000 kilometers in range. In 1979, the BTR-D was modified to operate the 92G Tusha smoke grenade launcher system. 2 launchers were affixed to each side of the vehicle. The projected 3D6 smoke grenades generate a 60-meter smoke screen with a duration of 60 to 130 seconds, and have a range of 300 meters. In 1979, Volgograd would design the BTR-D anti-tank missile carrier, which would be adopted in 1983. BTR-D operated the 9M113 ATGM, which could be fired at a rate of 2 missiles per minute. Inside the vehicle are a 9K111 and 12 additional missiles that are to be dismounted and operated separately. BTR-D replaced the Su-85 and the D-44 anti-tank gun. BTR-ZD, which entered service in 1984, was designed to carry anti-aircraft missiles, 20 of which were stored inside. The vehicle often mounted the Zu-23-2s supplied to the Airborne Forces out of convenience and increased flexibility. This started due to the fact the BTR-D was chosen by the troops as the preferred option for towing the Zu-23-2, as the GAZ-66 proved unsatisfactory. Eventually, during exercises, especially those that involved river crossings, the Zu-23-2 would be placed atop the BTR-D. This would allow for the system to fire throughout the course of thwarting a water obstacle. This eventually became standard practice no matter the circumstance, much to Volgograd's chagrin, as their representatives thoroughly objected to this solution. Because this was never a formally authorized modification, different units had different methods for mounting the ZU-23-2, which led to some less than elegant results aesthetically speaking. Notably when the ZU-23-2 is mounted towards the engine compartment, which can significantly decrease the cross-country capabilities of the vehicle. In the mid-1980s, the BTR-D would see the inclusion of the R123M, R173, and R174 intercom system, which would replace the older semi-transistorized radios. In 1984, the BREM-D was proposed, which was an 8-ton armored recovery vehicle. This vehicle would enter service and serial production in '89. I will avoid speaking about this system as it falls outside the time frame of this video. GTMU is a light airborne armored personnel carrier, which is considered an inexpensive alternative to BTR-D, and as a result occupied many rear service positions within the Airborne Forces. Command posts, chemical reconnaissance, and material support were its primary aims, though it could also serve as a troop transport if necessary. This is not encouraged as the vehicle lacks an integrated weapons system, and is therefore rather vulnerable. If you want to learn more about the RKHM-2, which is the chemical reconnaissance variant, I recommend checking out my video or article on the chemical troops. 1V-119, which sought to provide an artillery reconnaissance and fire control capability to the airborne forces akin to PRP-3, began development in the late 1970s. The system employed the BTR-D as its chassis, which expedited the R&D process as this vehicle already had an established reputation of excellence. In 1982, the vehicle would enter service, and that same year it would begin serial production. 1V-119, like PRP-3, occupied a myriad of roles, including terrain navigation assistance, general reconnaissance activities, spotting for ATGMs when operating within a defensive posture, limited chemical reconnaissance, and the transmission of target coordinates to artillery systems. When supporting batteries, 1V-119 is used as a mobile command post, which may be manned by the Chief of Staff or the senior officer of the battery. The Chief of Intelligence within an artillery regiment may also be assigned to a 1V-119 to conduct his duties and coordinate actions on the battlefield. In regard to onboard equipment, 1V-119 operates the 1RL-133-1 ground surveillance radar, 1D-11-1 laser rangefinder, 1PN-32 night observation device, GO-27 radiation and chemical alarm, as well as the 1G13M and 1G25 gyro compass, 1V520 ballistic computer for fire direction, 2 R123M radio stations, an R107M radio station, and the R124 tank intercom. 2 TA-57 field telephone sets are present alongside 500 meters of telephone line to establish the R107M in a detached position. A 6,000 by 9,000 millimeter camouflage net is provided to the crew that may be used to obscure the vehicle or a reconnaissance position erected by the crew. Stored inside for self-defense purposes, one can find an RPG-18 or a Strela 2M. Many of these systems and the roles of those who operate within the vehicle are described in my night fighting article, where I break down the PRP-3. In the early 1960s, the Su-85 was becoming increasingly antiquated, and towed guns were no longer an effective solution to offsetting the inefficacy of this system. To solve this complication between 1967 to 1968, 2 prototypes were proposed by Volgograd, which employed Object 915 as their chassis. These would be the 2S2 122mm howitzer and 2S8 120mm breech-loaded mortar. 2S2 was requested under the same decree, which would result in the development of 2S1, 2S3, and M240. In 1969, it was determined that the next generation of airborne fire support vehicles would use a 120mm mortar, as opposed to a 122mm howitzer. Research and development to design such a system was carried out between 1972 to 1975 at No-25 under VM Sabelnikov. F.F. Petrov was also involved in the design process. He would frequently propose the application of his 122mm M30 howitzer, which proved unsatisfactory due to the space it occupied inside the vehicle. At this time, V.A. Golubev at OKB-9 was working on the installation and development of the new 120mm mortar, which was to be mounted on 2S2. As this transpired, early experimentation, which would lead to the mounting of the prototype 120mm mortar, on Object 925 had already begun. The ammunition of this system was developed at NPO Basalt, which was headed by E.I. Dubrovin. High explosive fragmentation rounds were spearheaded by M.M. Konovayev and Y.G. Snopuk, while V.A. Piruev developed an anti-tank munition that would allow for the dual-purpose application of the new weapon system. The 120mm mortar, which would be selected for the project, had its roots in a towed recoilless system that had been in development for quite some time. Here it was found that a recoilless rifled mortar offered similar efficacy to that of a 152mm howitzer. The project was subjected to a great deal of scrutiny, and machines to produce ammunition which would allow the system to function were non-existent at the time. It would take some time to convince those who objected to the concept that this was indeed the future of mortars within the USSR, and that designs produced on the basis of Shavirin's guns could no longer be modernized. Rifled mortars featured greater accuracy and could operate heavier, more effective ammunition. After developing this mortar, it was necessary to determine a system in which it would be installed. This is how Margalov and Petrov got involved in the program and proposed its use on a new airborne artillery system. Of course, Petrov would push against the integration of this gun, but that was entirely a result of his own personal preference towards the howitzer he had designed. It is stated that the French MO-120 RT-61 provided a great deal of inspiration for the project. Eventually, after many heated debates, in 1974 a mock-up was devised, which would receive the designation Nona-D. Firing trials proved difficult, as due to a freak accident, a round exploded in the barrel a day before the vehicle was to be demonstrated. Luckily, the system was repaired well before this event was to transpire, after which the support of Margalov was won, and the vehicle was selected in favor of its competitors. Unfortunately, at this stage in the Nona's development, Volgograd backed out of the project, and refused to produce the vehicle. Despite this, the first version of the turret would see production in 1976, and by 1979 a battery to test the vehicle was assembled. The Airborne Forces were eager to get their hands on the new weapon system, so much so that they began using the Nona well before it officially entered service. When Nona was tested by those from the Artillery Academy, there was a great deal of skepticism present regarding the likelihood of a 120mm mortar creating a crater with a width of 5 meters, as was promised by the design team. After 2 rounds were fired, General Matveyev was so impressed he requested that a photo be taken with him standing at the edge of the crater created by the system. Nona would officially enter service in 1981. The Artillery Regiment of the 98th Airborne Division was one of the first to fully integrate the Nona in 1982. The vehicle employs the BTR-D as its chassis and retains its internal layout. Within the vehicle, the gunner is placed left of the gun, while the loader is located on the right. After 2A51 is fired, compressed air clears the barrel. This lasts 1.2 seconds. The Nona incorporates a hydraulic recoil brake, which ensures a recoil stroke of only 400mm. An experienced crew can achieve a rate of fire of 10 rounds per minute, though a more likely ROF is 4 to 6 rounds per minute. 25 rounds are stored inside the vehicle. Nona's gun can be adjusted vertically between -4 to +80 degrees. The 1P8 periscopic sight is employed for indirect fire, while 1P30 sees use in direct fire engagements. 1P8 can be used for direct fire in emergency situations if 1P30 is rendered inoperable. In cases of low visibility, the K1 cannon kilometer can be employed to engage targets with reduced accuracy. Systems are present which reduce the probability of errors occurring when operating the sight if the vehicle is at an angle or on the move. A level is present which provides increased redundancy. A terminal is available to the gunner, which is used to provide him with information supplied by the FCS. If the gun is elevated to an unfavorable position, which may endanger the crew, a warning light is lit to inform the gunner of this error, so that he may correct it. The other lights on the terminal assist the gunner in determining if the gun has been elevated to a correct position to engage his desired target. When all 3 lights are illuminated, 2A51 is ready to be fired. 1P30 features divisions which assist in direct fire with the various types of ammunition supplied to 2S9. When direct fire is to be engaged, the gunner turns the turret to face the target, after which he reports the range of the enemy using the divisions present on the site. 3OF49, the primary munition employed by Nona, has a steel body, and has an explosive mass of 4.9 kilograms. The round is capable of producing 3,500 fragments, with a mass between 0.5 to 1.5 grams, with a velocity of 1,800 meters per second, the largest of which can penetrate up to 12 millimeters of RHA, at a distance of 10 meters. The crater generated via the use of this round is often 2 meters in depth and 5 meters in width. 3049 can be fitted with a proximity fuse, which increases its effectiveness by 2 to 3 times. The round has a range of 8,800 meters. 30F51 has a cast iron body, with an explosive mass of 3.8 kilograms, and has a muzzle velocity of 367 meters per second. 30F50 is a rocket-assisted projectile, which engages its engine 10 to 13 seconds after leaving the barrel. 3BK19, which was introduced towards the conclusion of the Cold War, is a heat munition with a mass of 13.2 kilograms, and a muzzle velocity of 560 meters per second. 3BK19 has a range of 600 meters, meaning 2S9 would have to ambush its target. The round penetrates 600 millimeters of RHA, which is enough to threaten most MBTs of the era. The penetration of 3BK19 is roughly comparable to what 2S1 Gvozdyka is capable of achieving with its own heat round. Nona operates the R174 intercom system, which allows the crew to communicate with one another, and R123M, or R173 for long-range interaction. The vehicle is landed using the PRSM-925 retro-rocket parachute system, 3 of which are dropped from an IL-76. 2S9s were organized into batteries, which featured 2 Nona platoons and a command platoon, alongside a material support unit to ferry ammunition to the mortars. Such a unit could deploy in roughly 4 to 5 minutes. Each division had access to 2 to 3 batteries. Throughout much of the Cold War, the Soviet Airborne Forces were not afforded their own communication devices, and instead relied on specialist systems designed for operation within the Army. After their reorganization under the General Staff of the USSR, the Airborne Forces saw renewed investment, which meant the development of airborne radio systems became a possibility. This was only bolstered by the integration of mechanized elements, which meant that heavier communication equipment could be carried across all units, which allowed for greater range and flexibility. This removed the need to lay telephone lines between command installations, which increased the speed at which control elements could reposition, and more importantly meant that orders could be issued while on the move. Of the means in which airborne command and control could be improved, automation was indeed one of the most important endeavors. Automating aspects of the control process would increase the speed at which the airborne forces could deploy. 15 automated alarm systems were integrated within each regiment, and as a result deployment times fell to just 10 minutes. These alarms would sound regularly to uphold the readiness of these units. An experienced formation could assemble into columns within 4 minutes of receiving the signal, and within 12 minutes not one BMD was to be left at the base. The primary communication systems employed by the Airborne Forces included the R128, R154, R141, R152, R440, BMD-1 KSH, and BMD-1R. R128 alongside R254 were used to assemble units once a landing had occurred, and were exceedingly common in airborne formations. R128 was a beacon transmitter that broadcasted a single tone, which could be tuned from 44 to 50 MHz. R128 employed HKN-20 NiCad batteries filled with potassium hydroxide, starved electrolyte, which was common across most batteries present within the Warsaw Pact. R254 is a 600 kHz beacon receiver that exists to pinpoint the location of R128. R254 comes in 10 frequency variations. R154-2 entered service in 1960 and was produced by the Omsk radio plant, and is a long-distance communication device proofed against shortwave interference. The device can receive telephone and telegraphic signals, of which it can receive 2 simultaneously. High-speed telegraphy was enjoyed within the Soviet military, as it was rather difficult to intercept or interrupt. Telegraphic communications are recorded within the device and can be printed for later inspection. R154 has a frequency range of 1 to 12 MHz, and has 3 subranges. A sensitivity of 10 MV is present when operating in telephone mode, which drops to 2 MV in telegraph mode. The system weighs 100 kilograms, and therefore requires a mechanized transportation device to operate effectively. Compared to R250, R152 is the superior radio. This is evidenced by the quartz filters in the UHR, far greater stability, and the fact it was exceedingly simple, which made it relatively easy to repair in the field. R141 is a medium-power radio station mounted on GAZ 66B and BTR-D, which served in separate communication battalions. R140 is a semi-transistorized simplex shortwave transmitter, and was the primary mechanism by which the system operated. This device featured an output power of 1,000 watts, or 800 according to some sources, and a range of 1.5 to 30 MHz when operating in telegraphic mode. When operating in telegraphic mode, R140 has a range of 2,000 kilometers. When engaging telephonic communications, a range of 1,500 kilometers is present. R140's range is significantly reduced if two-channel single-band operation is engaged, due to the splitting of the system's power between two channels. Before an operation, the radio was tuned to 10 preset frequencies. This would define the range in which the radio would operate as it was used. Automatic tuning was present. R140 included the R155P and R311 receivers, a TA57 field telephone, and R105M, which had a frequency range between 36 to 46.1 MHz with a communication range of up to 25 kilometers. A signal-to-noise ratio of 20 decibels is present alongside a frequency departure of positive or negative 40 kHz. R152 is a portable high-frequency radio that was developed for use within the Airborne Forces, with a frequency range between 2 and 30 MHz. R152 allows for broadband telegraph 7x2 kHz transmissions at a speed of 25, 75, and 150 baud, as well as narrowband telegraph 7x2 kHz at speeds of 35, 75, and 150 baud. When employing the dipole antenna, R152 can achieve a range of 500 kilometers. This increases to 300 to 2,000 kilometers if the system's traveling wave antenna is used. The radio has a sensitivity of 3 to 4, and a transmitting power of 30 to 40 watts. R152 features a spurious emission suppression of 50 decibels. R440 is a rather unique system that was designed to solve an exceedingly difficult task, that being the effective transmission as well as reception of commands, information, and requests for support within strategic depth. Of course, the need for long-distance communication systems was by no means a requirement exclusive to the Airborne Forces, but such a capability was necessary to ensure that they were properly employed. In the 1970s, a complex that would become the solution to this problem was already under development at the Moscow Research Institute of Radio Communications, under the Unified Satellite Communication System program. At the outset of the project, USSS was to be a general-purpose device that would see integration across all branches of the armed forces. This communication system was to be entirely digital, immune to deliberate interference, and operate as a network across multiple vehicles with 1.5 to 2.5 meter antennas, in 9 to 11 directions simultaneously. Around 1975, the first iteration of R440 was delivered to the troops, mounted in GAZ-66, alongside PTC-1 and PTC-2 receiving plus transmitting centers, which would act as information handling control points. R440 would officially enter service in 1980, after which efforts would be made to increase resistance to noise jamming, throughput capacity, and flexibility. R440 had a frequency range of 4 to 6 GHz, which would be improved to 7 to 8 GHz via the introduction of R441. R440 is designed to interact with satellites in geostationary and elliptical orbits, which provide digital duplex telegraphic, telephonic, and telecode communication. A single R440-0 communication station provided communications in 2 directions, with a maximum transmission speed of 4.8 or 5.2 kilobits per second, which allowed for the creation of many high and low-speed channels. Low-speed telegraph channels with a speed of 50 baud would always be available in either direction. When operating in anti-EW mode, transmission speed decreases to 1,200 baud. One transmitter has an output of 130 watts. When transmitting, the frequency range of the device is broken into 10 trunks, each with 50 MHz. Alright guys, this marks the conclusion of the video. I have no script for this, but I wanted to say that thank you a ton for watching. It really means a lot. These videos take forever to put together. This video is a combination of work that has spanned a few months. I kind of dropped the topic for a while though, so that's why there's such a considerable gap in time, but you know. Also, consider looking at all the links in the description, because those are the primary means in which I post and communicate with people, so if you want to engage or anything like that, go check those out. And also, look out for part 2, should be coming out soon-ish. It's going to focus on light vehicles, equipment for infantry, doctrine and the application of everything I just described, and all sorts of other stuff like comparisons with Western Airborne Forces and how the VDV, yeah, you get it. Anyways, thanks for watching.